looked at 8 point, there's some mixing and solution in chapter 8. So we will be doing that maybe next week. Okay, inshallah. So right now, let's look at combustion. Everybody knows what combustion is. I'll be surprised if there's somebody that doesn't know. Combustion means the burning of fuel, the burning of anything that can burn. The fuel can be liquid, solid, or gas. The solid fuel, one example would be coal, arang batu in Malay. And if you have liquid, that would be crude oil or petroleum. If you have gas fuel, that would be natural gas. That's the most common, natural gas. For your cooking cylinder, gas cylinder, most of it is methane. Okay, so that is from natural gas. So as you can see from the screen, when you do combustion, the main aim of doing combustion is to get the heat. You wanted the amount of heat being released by the combustion inside the reactor or inside the combustor. So when you have that amount of heat, a very huge amount of heat being released, that will be used to turn turbines. And for example, to get electricity. Okay, so most of the combustion process involved in coal is in order to get electricity. Okay? So there's two types of combustion process, either complete or incomplete. If it's incomplete, that's where you produce carbon monoxide. So carbon monoxide is actually a poisonous gas. You can't see it, you can't even smell it, but it's a poisonous gas. So carbon monoxide is being produced, and there's lots of cases of people dying because of carbon monoxide poisoning. So that's a very dangerous gas. But most of the combustion process will be producing carbon dioxide, and that is a harmless gas. Well, not really harmless, because that is causing greenhouse effect, actually warming up our globe, our world, because of this accumulation of carbon dioxide. So we will be looking at combustion whereby it is complete combustion. So when there is complete combustion, you will have carbon dioxide gas being formed, you have water being formed. Okay? Beside that, because your source of oxygen is from air, so inside air you have 79% mole nitrogen, 21% mole oxygen. So you will have nitrogen coming out in your effluent, because nitrogen is not being consumed, neither is it being produced. So it will stay as it is, input equals to output. So your nitrogen will be in your effluent, in the output product. So what you have to do when we're looking at combustion, you be calculating the outlet temperature. That's one of it. And normally when you're looking at combustion, your fuel, because it is very expensive, you will let your fuel be the limiting component. Your fuel will be the limiting component, and that means your oxygen or your air will be in excess. And so we already look at how to calculate excess, how to calculate percent excess. So this is one example. This is the equation that you'll be looking at. Could be air, it could be oxygen. Either one is the same. You will come up with the same value of percent excess. So this is the amount coming in. I better highlight that. This is the amount coming in. This is the stoichiometric proportion, or that is the theoretical amount. So this is the stoichiometric proportion or the theoretical amount. So we have looked at this equation. So that's nothing new. So we will proceed to the discussion on heating values. You should come across to this. I'm not sure whether you have come across this before, but it is also being discussed in thermodynamic heating values. Heating values, as you can read from the note, is the maximum possible heat that you can get from combustion process, and that is per mole of your fuel. Your fuel must be 1 mole. The value that you can get from the heating value is the negative of the heat of combustion. The standard heat of combustion, negative. Your heat of combustion, if you look at the appendix, let's see, let's go look at our appendix. Where is my appendix? Okay. If you look at the appendix, this is appendix B2, it should be in B1. I'm not going to look at B. Okay, here is the heat of combustion. If you look at this appendix, your heat of combustion, they are negative. It cannot be positive because you are the process of combustion release heat. So it's exothermic. It always be negative. There's a typo error. I come across one value that is not negative. As you can see, it is negative. Okay? So one of it, I'm not sure what component it was, but it was written as positive. But actually, it should be negative. As you can see here, it should be negative because the combustion is an exothermic process. Here is one that is typo. There should be a negative sign in front of it, and it is for methanol. There should be a negative sign. So your heat of combustion is always negative. So when you look at heating value just now, the notes just now, heating value is always positive because your heat of combustion is negative. It is always negative. Okay? So your heating value is always positive. Your heating value is always positive. You should not be getting a negative value for your heating values. Okay, so the heating value, there's two types of it. Either a higher or a lower heating value. A higher heating value denoted by capital H, V, or a lower heating value denoted by LHV. There's two types of it. What distinguishes between the two is that the water phase. If you are looking at a higher heating value, your water should be in a liquid form. If you're looking at lower heating value, your water should be in a vapor form. So how to remember? I use this method. This is L. So L, normally you would think that it's going to be liquid, but no, it's going to get vapor. So that's how I remember. Your lower heating value is going to be getting vapor. You're going to get vapor when you're looking at the lower heating value. Okay, so the difference between the lower heating value and the higher heating value is this. This is your, sorry, I should not be highlighting. I want to write. That is your latent heat of evaporation. Latent heat of evaporation, which is at 25 degrees C, and that is normally 44.013 kilojoules per mole, that value. And that is your number of mole of water being formed divided by mole of fuel being burned. One mole of fuel being burned. Okay? So that is just like when you do the heat of reaction, remember? You got the equation written in terms of liquid water being formed. Let me write it down. For example, you have methane gas plus oxygen gas. I need to balance it. I know it's not going to it's not balanced now. Carbon dioxide gas plus liquid water. Another thing I need to remember, guys, the equation for heat of combustion, you always get liquid water. For the heat of combustion, you always get liquid water. Okay? So that thing you need to bear in mind. So if you get liquid water, that means that is the higher heating, higher heating value. Yeah? So your water is going to be formed as a liquid when you look at your heat of combustion in the appendix B1. So now, if you get this value, for example, for methane, not sure what's the value, but I have somewhere written here. If I look it up, first for methane, then look it up in your appendix. The value is 802 minus 802. I'm not sure if it is. It's 802. That's kilojoules per mole. Let's have a look at our appendix. Is that correct? For methane, Oh, no, sorry. It's 8 minus 890.36. That must be, I got a mistake there. Minus 890.36. So let's go back. Minus 890. I made a mistake there. Let me correct it. Minus 890.36. Oops, sorry. I cannot write anymore because I'm already at the border. Yeah, so that's 0.36. Okay. That is kilojoules per mole. So that is your heat of reaction, the same as your heat of combustion. Your standard heat of reaction is the same as your standard heat of combustion because that is the reaction going on here. So let's balance our equation. You have one carbon on the left hand side, you have one carbon on the right hand side. That's done. You have 2 hydrogen on your right hand side, so you need another 2 in front of water. Yes, so I need to undo. I need to undo this part because I don't have enough space. Carbon dioxide plus 2 water. Okay, plus 2 water. And oxygen on the right hand side, you have 2 plus 2, 4. So that means that there must be a term, there must be water, stoichiometric coefficient for water over here, oxygen over here. So what is that going to be? You have on the right hand side 2 plus 2, 4. So that's going to be 2. Is that correct, guys? Is my equation balanced?
Yes, doctor.
Thank you. Okay, so from that balanced equation, your heat of combustion and your heat of reaction is minus 890.36. Okay? So this is actually your forming liquid water. You're getting liquid water, so that is actually your higher heating value. It must be positive. That is the negative of your heat of combustion. So that's going to give you 890.36. That is your heating value, your higher heating value. So now going back to this equation, to that what I was going to say just now. If you're going to remember last time I pointed out that if you wanted to get water at the heat of reaction for this reaction, the same heat of the same equation, except that now you're going to form water vapor. Remember last time when I mentioned that in order to get this value, your heat of reaction, how are we going to do that? Do you remember? Anybody?
You add the 44 point something.
Yeah, that's it. Okay, so let's go back to that part of this is at the very beginning of the chapter actually. I'm going to need to scroll up further at the very beginning. Somewhere there. Okay, you need to add up that value. That value actually is 44.013. NW is equals to the mole of your water formed divided by 1 mole of your fuel. The same thing as what I just mentioned just now. Okay, so that's actually is the same as the equation, the difference between the higher heating value and the lower heating value. So let's go back to our slide on heating value. Oh yeah, guys, I need to mention, before this, I have over here the example from chapter 4. The reason I have it in the slide is for you to recall back how to do multiple reaction. You need to review, you need to review how to do multiple reaction because you're going to encounter it in your energy balance. So you need to know how to use atomic balance or extent of reaction in order to solve your matter balance. So let's go back to this problem again, to this statement. Your heating value, this is actually that N times by the latent heat. That's the number of mole of water per 1 mole of fuel, the same as just now. Okay, and this is 44.13. Okay, so if I want to get that this heat of reaction, oops, I erased it. I wanted to highlight it. If you wanted to get this heat of reaction, no, I mentioned that before. All you have to do is get the minus 890.36 plus NW 44.013. Isn't it? That's the same thing as what you're doing over here. That's the same thing what you're doing over here. Yeah? Your N is the number of water formed. This part of the equation. Okay? Number of form. So in this case, you get 2 times by 2. Your number of water form is 2, and your fuel is 1. There's only one. There's 1 there. So you get minus 890.36 plus 2 over 1 times by 44.013. Okay, so when you do that calculation, that's where you get 820. I got let's see, what did I get? 802 is now the value that I gave you guys. 802 kilojoules. Don't have enough space. Kilojoules per mole. Yeah, minus. There's a minus sign there. Yeah, so that's the same thing as what is written here. You're getting vapor. You're getting vapor here. You're getting vapor. So that means your vapor is your lower heating value. You're getting vapor here. Your lower heating value is the one where you produce water vapor. So that L, lower heating value, is the negative of the heat of reaction of combustion. In this case, it's combustion. You know, the heat of reaction is the same as the heat of combustion because the process is combustion. So you get 802 kilojoules per mole. That's the same thing. This equation is actually how to get this. I know the difference between these two reactions. That's the equation. That equation is actually a difference between the two equations. One of it is forming water vapor. The other one is forming liquid water. That is actually what it's all about. Yeah. So your latent heat of combustion, this is in kilo SI unit. Okay, or in terms of kilojoules per mole. This is in terms of kilojoules per kilogram, and this is BTU. That is the English unit. Right. So if you have a mixture, for example, natural gas, you have methane, you have ethane, you have propane. So when you have a mixture, regardless of whether you're going to get your higher heating value or you're going to get your lower heating value, either one of it will be obtained using this summation. This is going to be either mass fraction or mole fraction, depending on what is your unit for your heating value, or for the individual heating value. This is the individual heating value. So if you're going to calculate LHV, then the bracket will be, for example, XI, then that will be LHV, your lower heating value. If we're going to get higher heating value, then your summation will be the product of your mole fraction with your the individual heating value of every component in your mixture. As I mentioned, in your natural gas, you have ethane, you have propane, you have methane, all that. Each component in your natural gas should have its individual heating values. Okay, so you sum it up. So let's look at one example over here. Okay, this example, your standard, this is actually butane being burned with oxygen. This is a complete combustion process. You have carbon dioxide being formed, and you have water vapor. So your heat of reaction for this case is given negative 2658 kilojoules per mole. Yeah? So that is going to be your heat of reaction. Is also the same as your heat of combustion because this process is a combustion process. The question asks, what is the higher heating value of this reaction, of this combustion? Right? So remember, the higher heating value, you just have to remember, higher heating value, you should be getting liquid or vapor for water. Anybody?
Liquid.
Liquid, thank you very much. Liquid water. So, but this reaction, the one written here, is you're getting gas. So that means that value over here, if you change it to positive to negative, that will be your lower heating value. That is going to be your lower heating value, 2,658 kilojoules per mole. That is your lower heating value because you're getting vapor. So the question asks for a higher heating value. So the higher heating value can be obtained using this equation. This equation written in highlighted in green. So to get your higher heating value, you must add your lower heating value to the number of mole of water being formed for every 1 mole of fuel times by the latent heat of vaporization of water at 25 degrees C. So if we do that calculation, 2658 plus the number of mole of water here is 5. Your fuel is 1, so 5 over 1 times by your latent heat of vaporization in terms of kilojoules per mole is 44.013. So if you do that sum, you should be getting that value, 2878 kilojoules per mole. So please check, is it actually 2,878? Is it really exactly that amount or is it a round off value? Let's do the calculation. 5 times 44.013 plus 2,658, you'll be getting 2,878.065, 3.1. Round it off. Okay, so that's the answer, the same as the answer, the solution. So part B. Part B, if the fuel contains 40 watt% hydrogen having a heating value of 143, higher heating value. Your other component is methane, 60%, having a higher heating value of 55. Now, what is the heating value of your mixture? So if you're going to do that calculation, you need to use the summation here. This part in green, let me erase this so that we can see it in its original state. Okay, so this is your equation. That's the equation in green. Okay, so we're going to do this. You are the composition is in terms of wet percent. So your unit for your heating value is also in wet percent. That not wet percent. I mean per gram. So find the unit will cancel off. So now let's calculate HHP for that mixture. This is part B. You have 0.4 times the value of its heating value for your hydrogen gas, 143, plus 0.6, that is for your methane, with a value of 55 for its heating value. So when you do that calculation, you should be getting 90.2 as given in the solution. So let's do the calculation to see is it exactly 90.2. Okay, exactly 90.2, and the unit is kilojoules per gram. So bear in mind, if you do the calculation whereby you have a mixture, make sure that the unit will cancel off. If it's in mole percent, then your unit for your heating value should be per mole or per kilomole. Then it will cancel off. Yeah, so in this case, it is cancelled off. Okay, that's your heating value for this example. Any questions? Any questions? That's the amount of heat in given of, yes.
The lower heating value will always be the same number as the heat of reaction?
Yes, because your heat of reaction, when you look at the back of the textbook, is always in the appendix. The water being formed is always liquid. Yeah. So because lower heating value, sorry, did I get mistake again? Lower heating value, the lower heating value, sorry, I got mistake here. Higher heating value is always the water being formed is always liquid. Higher heating value. Remember, do not get confused. Okay, higher heating value, the water being formed is always liquid. It's always liquid. It's always liquid. So from the appendix, that is your heat of combustion. Yeah, so do not mix up with the higher heating value, because the higher heating value. So do not mix up with the lower heating value. Lower heating value, you'll be getting water vapor. Right, so just remember. If you don't remember, just look at your textbook or the notes. That's easy. So let's proceed with this example. 961. Let's see whether I have it written here. Example 961. Okay. Now you have a natural gas, having the methane and ethane. The composition is 85% volume by volume. That means you can change it to mole. The percent is actually molar percent. This is 15% for ethane. And the heat of, because it's a mixture, you have the two equation. One of it for methane, the other one is for ethane. Okay, and this is your heat of combustion from the appendix, as written from the appendix, and it's written over here. The heat of combustion, okay, at 25 degrees C and 180 M. So you're going to get, this is actually water vapor, guys. It's not from the appendix. If it's from the appendix, it will be liquid water. But this is vapor. So let's look at our textbook. Methane. Just now we got a value for methane when we were looking at the notes. Where is methane? Okay, there. That's methane. I got minus 890.36. So the one that is given here, minus 802. That's the value we calculated earlier, isn't it? We got minus 890 from the textbook, from the appendix. There, that is the heat of combustion from the appendix. We calculated, when you have water vapor form, we got that value. So this is actually the value we calculated earlier, okay, for methane, minus 802. So let's go back to my example. Okay. So the water is in a vapor phase. So what is it? What heating value is it? Is it higher or is it lower? If you have water vapor, is it higher heating value? Lower. Thank you. Lower. It should be lower. Yeah. So lower heating value for methane is equals to 802 kilojoules per mole. I'm getting that value from the heat of reaction given, or the heat of combustion. And the lower heating value for ethane is equals to 1428. The value must always be positive. Right? So this is your lower heating value. But the question is asking, the statement here is asking for a higher heating value. The unit must be in kilojoules per gram. Over here, the unit is per kilojoules per mole. Obviously, you're going to change something. You're going to convert the unit. Okay, so now, we're going to stick with kilojoules per mole first, because the composition is in terms of volume. When it's percent volume, it's the same as percent mole. So that means for your composition of, let's see, I'm writing here, Y, for methane, it's going to be 0.85. Don't use Y because the textbook uses X just now, so I better change that. I'm so used to Y because Y is when it is a mole. Yeah, so but the textbook just now, the equation written is using X. So for ethane, so we're going to stick with X. That's going to be 0.15. That is mole per mole. Okay, so if we're going to calculate the lower heating value, get the lower heating value first, use the summation just now, whereby you have summation X times by the lower heating value of each component. Right? So I'm going to do that. You got 0.85 for your methane, with the corresponding lower heating value, and your ethane and its lower heating value. So when you do that calculation, let me see whether I have here. I did this earlier. What did you guys get? What's the answer? Anybody? Nobody? Nobody going to respond? Let me calculate that.
Doctor, 800
800
and 95.9.
95.9. Thank you. That the unit is kilojoules per mole. That is your lower heating value. Okay? That is your lower heating value. If you're going to do your, let me see how I'm going to get this. That is your lower heating value, but we wanted a higher heating value. How are we going to get our higher heating value, guys? Anybody?
Doctor, we get the height of vaporization for both components.
For the first component, the HL first. Okay. For H, higher heating value is equals to lower heating value plus the number of mole of water being formed times by 44.013. So if we do that calculation for ethanol, for methane, that will be 802. That's the equation here. You have 2 mole, okay, for ethane, for methane. So that's 2. So you can end up with 890, is it? And you do the calculation. High heating value of methane. This is your lower heating value. That is your high heating value of methane. So if you do the same thing for ethane, that will be your 1428 plus the amount of water being formed here is 3. Okay, so that's 3 times by 44.013. That will give you a value of 1560.039. That's what I got. Double check my calculation, please. So that is another way of doing it. So once you get that, your higher heating value, use the summation rule, 0.85. For methane, 890.026 plus the mole fraction of ethane times by its corresponding higher heating value. For ethane, you will get an answer of 990.53. That's what I got. Kilojoules per mole. Okay, that is in kilojoules per mole. The statement asks for the higher heating value having a unit of kilojoules per gram. Okay? So what you have to do is you have to get the molecular weight of your gas, of your natural gas. The molecular weight of your natural gas, you can get it using this formula. Yi, molecular weight of I. Can do that. Okay, so in this case, you have methane, 0.85. The molecular weight of methane, if you look it up inside the textbook, or if you can calculate it using the formula itself, C is 12 plus 4 hydrogen, so it will be 16. But if you look it up in the appendix, it's 16.04. Okay? And then the mole fraction of ethane is 0.15. The molecular weight of ethane, if you look it up or you calculate it using its formula, is 30.07. This is from the appendix B1. That is molecular weight. This is molecular weight of ethane. That's the molecular weight of ethane. So when you do that, you come up with a value of 18.1445. Okay? So that can be written as gram per mole or also can be written as kilogram per kilomole, or can be written as pound mass per pound mole. The same value, 18.1445. Okay, so now because our unit is per mole, so we're going to change that. Your higher heating value having a unit of per gram is going to be 990.53 kilojoules per mole. So 1 mole of your natural gas, the molecular weight is 18.1445 gram. So I need to erase this. Okay. And that's going to give you your unit kilojoules per gram. So when you do that calculation, you will get what? 54.591. That is your higher heating value having a unit of kilojoules per gram. So that's the answer for the problem. Let's look at the answer. Is it given here? Okay, that's the answer. 54.7, but we got 54.6. Slight difference. And we got 54.6, but the solution given is 54.7. So you can do it this way, slightly different from the solution from the textbook. It's also the same. You can get the same answer. Any question, guys? How to get the heating value if you are given the equation? The equation is given. Since this is in terms of vapor, so that will be lower heating value. So this will be lower heating value. That is your lower heating value, but it must be negative heat of combustion. Then it must be negative heat of combustion because that is heat of combustion. Any questions? Anybody? Any questions? If you're not sure how to go about it, have a look at your textbook. Sometimes you guys don't want to ask, don't know why. If you are all clear about it, fine. I have no problem if you don't want to ask, because that means you understand it.
Doctor,
Yes.
Doctor, why are we finding the lower heating value again if it's given in the equation above?
We're not getting the lower heating value, we're getting the higher heating value. It is the higher heating value of the mixture. The value here is the lower heating value of the individual component, not the mixture. This is the lower heating value of the individual component in your natural gas. What the question asks for is the higher heating value of that natural gas. You can get the individual heating value, the higher heating value of the individual component from the appendix, no problem. After that, you just multiply it with the mole fraction. In fact, you don't even have to use these two equations here. You can get the heat of combustion from the appendix. You should be able to get it from the appendix because your appendix will give you the heat of combustion having water as a liquid. So when it's a liquid, then this will be your higher heating value. Your heat of combustion. Does that answer your question?
Yeah, it answers.
Okay,
Thank
good.
you, Doctor.
Welcome. Any other questions? Any other questions? No? Okay, let's look at one more example. Is there any example that is related to heating value? Okay, this one. Okay, in this example, let me see. Let me highlight. You have again a natural gas having 87.5% volume by volume. Obviously, that will be percent mole of methane. The other component is ethane, 7%, ethane, right, 7%. The other component is propane, 2%. And lastly, you have nitrogen, but nitrogen do not participate in combustion. Nitrogen is just an inert. It doesn't involve in the reaction. So now the question asks for what is the higher heating value and the lower heating value for this fuel. The unit must be in kilojoules per mole, using the heat of combustion from the appendix B1. And the second part of it is calculate the lower heating value of this fuel in having a unit of kilojoules per kilogram. So what we have to do is we got to write the equation for every component. Okay, for every component, you have, let's see, you have methane, CH4, burn with oxygen to form carbon dioxide plus water. So your heat of combustion, you can get it from the appendix. The heat of combustion, I have it somewhere written here. Just now we have we got it earlier when we were looking at the appendix. Let me see. Appendix is given the value is negative 890.36. That's the value from the appendix, kilojoules per mole. Okay, so that is your heat of combustion for methane. So let's balance. Just now we did this example just now. How? Somebody tell me these two. Is that correct? Because hydrogen over here is on the left hand side is 4. So you wanted the hydrogen to be also 4 on the right hand side. So your oxygen now is 4. So this should be 2. Okay, that's balance. So next we have methane already done. Ethane, C2H6 plus oxygen. You're going to form carbon dioxide plus water. Okay, now let me write this as liquid, because you know whenever you get the heat of combustion from the appendix, your water must be in a liquid form. So let's see, you have 2 carbon, so let's write down that's 2. Your hydrogen over on the left hand side is 6. So in order to get 6 on the right hand side, times by 3, so that will be 6. So now, how many oxygen do we have on the right hand side? You have 4 for carbon dioxide. 4 plus 3, that's 7. So that will be 7 over 2. Is that balanced? Somebody check. Next, we have propane plus oxygen going to form carbon dioxide plus water, liquid form. Okay. You have 3 carbon, so that's going to be 3. You have 8 hydrogen on the left hand side, so that's going to be 4. So now, what's the number of oxygen do you have on the right hand side? On the right hand side, you have 6 plus 4, that's 10. Is that 5? Is that correct? Done. So that's done. So now get the heat of combustion from the appendix for ethane. So if you look it up, you should be getting a negative sign for your heat of combustion. So if you look it up in the appendix, that's going to be 1559.9. I'm not going to show you guys how to get it in the appendix, because we have been looking at lots and lots of the appendix for all this while, so you should know how to get it. Minus 2220. All of these components, they are in the gas phase because it's a natural gas. So this is listed as gas. Your methane, your propane, your ethane is gas. So you should be looking up the gas form for your heat of combustion. So that's gas, that's gas, that's gas. So you have completed that part, but that is actually not what is required. You need to find the higher heating value and the lower heating value. So you need to do it just like the example previously. So I don't have enough space here. So what you have to do is you have to do, actually, what is the value of the heat, what is that given for, what is that value actually? Is that the lower or is it the higher heating value? Anybody?
Lower, Doctor.
You sure?
Higher heating value.
Higher, Doctor.
Higher, please. Please remember, if you have L, you're going to get water vapor. Yeah, so these are all higher heating values. So all you have to do is use the summation, higher heating value equals to the summation X times by its heating value. I'm not going to write the higher there, but it can be both. It can be either one of it, could be higher, could be lower heating value. Okay, so this is going to be, we're going to use our methane 0.875. Your higher heating value for this gas is going to be higher. So we're going to put right higher. Okay, so 90.36. Why is it positive? I already explained it should be positive. It's always the negative of the heat of combustion plus your composition for ethane 0.07, 1559.9 plus the composition of your ethane already done, propane 0.02, and that's 2,220. You do not include that of nitrogen because nitrogen is not a fuel. It doesn't participate in the combustion reaction. So do not include your nitrogen. So once you have calculated that, let me check my answer. What did I get? You can also calculate it yourself. You should be able to get a value of 932.375. Round it off to 3 decimal places. And that is your higher heating value for that natural gas. I don't have the answer here. So that's the value I calculated. So now if you want to get the lower heating value, you have to calculate for every equation. For these 3 components, you have to calculate its lower heating value. So you need to use this formula, higher heating value. I'm going to write it over here. Is equal to lower heating value plus the number of mole of water being formed for every 1 mole of fuel times by the latent heat of vaporization of water at 25 degrees C. So if you're going to write for methane, the lower heating value, we're going to rewrite this equation is equal to the higher heating value minus n times by 44.013. So for the I need to have more space actually. Okay, I'm going to for methane. So my lower heating value for methane is equals to, already here I got 890. Okay, that's my high heating value. Minus the amount of water being formed. The mole of water being formed is 2. So minus 2 times by 44.013. So you should be getting, if you calculate it, what is that value? It should be 802.34 kilojoules per mole. That is for ethane. You do for methane and propane, the same thing. For now, I don't have enough space. Let me go higher then. Okay, the lower heating value of ethane is equals to, we got that let me circle that. We got that 1,559.9 minus the number of mole of water being formed for every 1 mole of fuel, that's 3. So minus 3 times by 44.013. So if you do the sum, you should be getting 1,427.87. So that's kilojoules per mole. That is your lower heating value for ethane. You do the same thing for propane, C3H8. So for propane, over here we have that is your heat of combustion. But your heat of combustion is actually your higher heating value with a positive value. That's going to be 2,220 minus the amount of water being formed is 4 mole of water for every 1 mole of propane being burned. So that is minus 4 times by 44.013. So you will come up with a value of 2,043.96. That is your lower heating value for propane. So if you are asked, for this case, the lower heating value of this fuel, that means the mixture, all you have to do is use this summation part, use this part of the equation. Instead of higher, now it become lower. It's become lower, that become lower. Okay, so this is lower heating value, summation, the mole fraction, and lower heating value. You do the same thing, except that now, so now I'm going to erase this value because I'm going to calculate the lower heating value. That is, I'm going to put in the value for the lower heating value. In this equation, I will get the calculated values from above here. For methane, that's the value 802.34. 802.34. For ethane, that's ethane. Okay, that's for ethane. The lower heating value of ethane 1427. Oops. 1427.87. And for propane, that's the value 2043.96. Right. So when you do that calculation, your lower heating value for this gas, what is it, guys? Anybody? Can you get anybody getting the answer? I got 843. Is it the same as you guys? Is it the same? That is, sorry, I need to erase this. This is not higher, it's lower. This is lower heating value. Anybody getting that same value?
Yes, Doctor.
Thank you. That is 843. That's the lower heating value. That's how you do it. So let's see. We already done part A. Part A, we got the unit in kilojoules per mole. We got both values of higher and lower. So for part B, you just need to get the lower heating value having a unit of kilojoules per kilogram. Now, all you have to do is get the molecular weight of your gas, of your mixture. The molecular weight of your mixture, the natural gas, in this case, is equals to the summation of the mole fraction times by individual molecular weight. So in this case, it must be in mole fraction. So you get 0.875. That is the mole fraction of methane. The molecular weight of methane, previously we already done this. The molecular weight of methane is 16.04. You can get this from appendix B1. Now the composition of ethane is 0.07. The molecular weight of ethane, somebody, is 30.07. That's ethane. Now you add up the molecular weight of the part for propane, 0.02. That's the mole fraction of propane. The molecular weight of propane, if you look it up in the appendix, is 44.09. And since you have nitrogen here, you still need to include nitrogen because you are calculating the molecular weight. So 0.035, and the molecular weight of nitrogen is 28.02. So if once you have calculated everything, your molecular weight for that mixture is going to be 18.0024. So it can be gram per mole, it can be kilogram per kilomole, or it can be pound per pound mole. So now that is your molecular weight for that mixture. So since the question part B asks for the lower heating value using having a unit of kilojoules per gram, so now we're going to look at the lower heating value that we got just now. We got this value 843 kilojoules per mole. So I'm going to erase this part of the unit because I'm going to write it so that it can be written kilojoules per mole over here. And I will multiply with the molecular weight of my mixture. That is 18.0004. It's divided actually because I wanted the gram over here. The mole. The mole should cancel off. Right? Mole should be here. And that's 18 point. My answer just now is 0024 gram. Cancel the mole. You will end up with a value of 46.827. Is that correct? Kilojoules per gram. Okay, let's check. 843 divided by 18.0024. That's the answer, 46.827 kilojoules per gram. So that's your final answer for part B. Okay? Your value for your light heating value, your lower heating value, that's the answer for part A. I already erased. Anybody? Any question? Omar?
The question asks the unit kilojoule per kilogram.
Kilogram. Okay. Now change this to kilogram then. Then if you change it to kilogram, then this will be 10 to the power 3 gram kilogram. Then it will be, okay, my answer is correct actually. My answer is correct. Okay, that's times 10 to the power 3 gram. Let me tidy up a bit. So that you can see what I'm doing over here. Sorry, thank you, Omar, for pointing that out. I thought it was per gram. Actually, it's per kilogram. So 10 to the power of 3 gram is 1 kilogram. Okay, so I need to write down my answer. That is still the same as 46. Is it 46? No, it's not 46, isn't it? It's 46,827. Because you already multiply it by 1,000. So the unit will be kilojoules per kilogram. You cancel this gram. Okay. So the answer now is 46,827. That's your final answer for part B. For part A, I already erased the higher heating value, but the lower heating value is 843. Any questions? You are actually just playing with this equation. This equation and that equation. You're just playing with that two equations. You must know that the heat of combustion from the appendix, you are forming liquid water. So if you're forming liquid water, that means you are getting the higher heating value from that heat of combustion, positive value. Okay, guys, any questions? Any questions? Why do I need to write the equation? Why do I need to write the equation? Because I need to have it balanced. I need to know the amount of water that is going to be formed. Because I need to multiply it with the latent heat of water at 25 degrees C. And that's what I did over here. So, any questions? Okay, that part is quite new to most of you guys. I'm sure you haven't come across it before, but you'll be looking at it again in thermodynamics. I'm not sure when you're going to cover it, but you'll be looking at it again in thermodynamics. Any question before I erase this? Because it's already overlapping on the next topic. Any questions? Okay, no, good. So I'm going to erase it because I need to cover adiabatic flame temperature. Adiabatic flame temperature. Adiabatic flame temperature is actually the out temperature, the T out of combustion. After you have done your combustion process, the T effluent or the outlet temperature is actually the adiabatic flame temperature. Why is it referred to as the adiabatic? Because you're going to do this in an adiabatic reactor, whereby the amount of heat is not going to be lost into the surrounding. And the amount of heat that you're going to get from the combustion process is going to be still inside the reactor. It's going to heat up your product, and part of it will be taken off for other uses. For example, for turning the turbine. Okay, so your adiabatic flame temperature is actually the highest possible temperature that you can achieve. Why is it the highest possible? Because no heat is going to be lost to the surrounding. Q is equals to 0. So that is the maximum possible heat that you're going to get in your product, the amount of your outlet stream. Okay, that's the maximum possible heat achievable. So that is the adiabatic flame temperature. Don't worry about this part. We have done actually how to calculate the outlet temperature. So it's actually the same. Actually, the only difference is that now is for combustion process. Right, so it's now all about combustion process. It has that's why it is referred to as flame, adiabatic flame temperature, because we're looking at combustion. Okay, so let's look at this example. 962. I think we should be able to cover that for the next 1 hour. Not really 1 hour. We're going to just need about 50 minutes or less than that. 96. Where is 962? Here you are. Yeah. you have liquid. Let's look at the problem statement. Oops. You have liquid methane. You have liquid methane. You're going to burn it with 100% excess air. Every time you have excess air, you know you're going to burn completely your fuel. You're not going to have any fuel left because your air is in excess. That normally that should be the way it should be ideally. But sometimes your fuel just remains unburned. But ideally it should be completely burnt. Okay? The statement the statement said that your methane is going to be fed at 25 degrees C, and the air that is going to supply your oxygen is going to come in at 100 degrees C. So the question asks for the highest possible temperature that the furnace wall can withstand. That means you have to design your reactor so that it can exceed and so that it can withstand that temperature. The temperature inside the reactor. If it cannot withstand, then definitely your reactor is going to explode. You have to design your reactor in such a way that it can withstand the highest possible temperature, and that is going to be your adiabatic flame temperature. Okay, so let's do this problem. We need to draw our block diagram first. This is your reactor. It's going to be adiabatic. You have your inlet coming in, which is your liquid methane. Let's assume a basis of 1 mole, because when you do 1 mole, just like you don't have to worry about the equation. I mean, better use 1 mole. That's easier. The 1 mole of methane, not methane, sorry, methanol, liquid coming in. You're going to have A coming in that is going to supply your oxygen. So you have A over here. We're not going to write, you can write N mole, but I'm not going to write it as A. I'm going to write it as oxygen. So I'm going to have N 1 mole oxygen and N2 mole nitrogen gas. But remember, the ratio of your oxygen and your nitrogen, you should know 0.21 mole fraction of oxygen, and the rest will be nitrogen. That is a simplified composition of A. Okay? And you're going to form your product coming out. This product will contain oxygen. Let's use a unit of N3, for example, mole oxygen, a symbol, N3, and 4 mole carbon dioxide, and 5 mole of water vapor. Why is it water vapor? Obviously, it's going to be water vapor because it's the highest possible temperature. It will exceed the boiling point of water. Okay? So your highest temperature definitely will be exceeding the boiling point of water. So your water will be in a vapor phase. And lastly, you're going to have your nitrogen coming out. Your nitrogen, you fed it together with oxygen, alongside oxygen, because you're getting your oxygen from A. So you have nitrogen there. And you're going to get it inside your effluent too. So beside that, you're not going to have any methanol coming out because it's going to be completely consumed. So what is the adiabatic flame temperature or the outlet temperature? That's the question. Okay, so our basis, we're going to have 1 mole of liquid methanol. Fed. Okay, so now we're going to do our material balance first. We're going to construct our table. I'm writing a straight line there. Yeah. I have input. I'm going to do this using the extent of reaction method. That's the input. That's the reaction. And this is the output. The row of output. So let's not a straight line. Can I get a straight line? I'm not getting a straight line. Okay. Here is my input, the number of mole, the unit is mole. My reaction, positive, negative, the coefficient in front of the symbol, and my extent of reaction, the unit is also in mole. My output, you should be familiar with this. If you are very comfortable with the extent of reaction method, if you are asked to do the problem to solve for the energy for the material balance, if you want to do it using the extent of reaction method, go ahead. If the question, the statement in the question did not specify what method to use, so just proceed with whatever method you find easier. So you have coming in methanol. Yeah, that's methanol. Okay, I have oxygen. I have nitrogen. I have carbon dioxide being formed. Lastly, I have liquid water. Not liquid water, water vapor. Yeah, I'm not going to write it as water vapor. I just leave it as water. So what do I have? 1 mole. And I have N1. I can calculate the amount of oxygen later on because the extra information given is 100% excess. So I'm not going to fill that up. I don't have any carbon dioxide being inside the input, and there's no water. Let's look at the equation. Is there any equation? No, you need to write the equation. You have ethanol being burned with oxygen to form carbon dioxide plus water. Okay, so that's the equation. You have 1 carbon on the left hand side. You should also be having 1 carbon on the right hand side. You have 4 hydrogen on the left hand side, so you should have 2 in front of water in order to make it 4. Now, how many oxygen do you have on the right hand side? You have 2 oxygen plus 2, that's 4. So you have 1 in over here, so you need 3, so 3 over 2. Okay. So your oxygen is balanced. You have 4 oxygen on the left hand side and you have 4 oxygen on the right hand side. So that's balanced. So I need to get the stoichiometric coefficient. This is going to be in front of methanol is going to be 1 minus 1. That's your extent of reaction. In front of oxygen, 1.5 is going to be consumed, so it's going to be minus 1.5 my extent of reaction. In front of carbon dioxide, that's 1. So there's no reaction for nitrogen because nitrogen doesn't participate in the reaction. For in front of carbon dioxide, this now is 1. So because it is being produced, it's positive. And also for water, you have water being produced. The coefficient in front of water in the equation is 2. So that's done. We need to balance it. Make sure you know how to balance your equation. So that's done. The information says that it didn't mention, but obviously you 100% because you are supplying 100% excess A, so your methanol is going to be completely consumed. That is also the same as oxygen. So your methanol is going to be completely consumed. So there's no output, or there's no methanol in the output. So obviously, if 1 minus 1 is equal to 0, this is going to be 1. So you know your extent of reaction is going to be 1 mole. So everything inside the bracket is going to be 1. So now, the fact that you have the statement 100% excess A or oxygen, so you're going to write that using the equation given, the number of oxygen or A in minus the number of oxygen in stoichiometric proportion or in the theoretical amount of oxygen that you need to supply. So let's look at the equation. If you have 1 mole of, I'm going to write this using a red marker. If you have 1 mole here, how many mole of oxygen should be participating? If you have the amount of oxygen and methanol, it should be in proportion. If you have 1 mole of methanol coming in, how much of oxygen should be supplied? Anybody?
1/2.
1.5, yes, 1.5 mole. Exact in proportion. That is the amount that should be supplied. So if we put that value inside this equation, this is equals to 1.5. That is equals to 1.5. You already supply 1. So you end up with actually times by 100%. because it's in percent. We cancel that 100, cancel that 100. So you end up with the number of, okay, I forgot, sorry. I made a mistake. It's not going to be 1. That's the unknown that you're going to solve for. Okay, let's rewrite this. I need to tidy it up. Okay. What is this value equals to, guys? If you have 100% excess, what is this value going to be? Equals to what?
3.
No. What's the number in front here? Before you calculate it first.
100%.
1.
1. Okay, that's 100%. So now N oxygen in is equals to 1.5 plus 1.5. That's going to be 3 mole. That's how you get 3. Is the fact that this is 1 because it's 100% excess. So we're going to get 3. So oxygen here is going to be 3. So N2, if you use this ratio, you should be able to get what is N2. Because you have 3 mole. So now I'm going to do this calculation over here. 3 mole of oxygen. Okay. I'm going to, zoom it in. 0.21 mole oxygen. That's the ratio of the mole fraction in A. Going to have a corresponding ratio for the corresponding mole fraction for nitrogen. Cancel that. You're going to get your mole of nitrogen. If you do that calculation, you should be 11.28. Thank you. Yeah, so that's going to be 11.28. So now we're going to fill up that value, 11.28, and your oxygen is now 3. So if you do the sum, 3 minus 1.5, you end up with 1.5. 11.28 plus 0, 11.28. 0 plus 1, it's not 0 because there's no carbon dioxide in the input. You're going to get just 1. And there's no water in the input. You're going to produce 2 mole of water based on the reaction, return reaction. So you're going to get 2. So that is the amount of output that you're going to get. So if you write it inside you can write it on here. That's going to be, and 3 is going to be 1.5. You can write it 1.5. And 4 is going to be your carbon dioxide. It's going to be 1. And 5 is your water. That's going to be 2. And your nitrogen 11.28. If you want to write it down. If you don't want to, obviously you can read it from the table. So that's your material balance. Now, the question asks for what is the outlet temperature. So you need to do your energy balance. So in order to do your energy balance, you still need to construct your table. That's what we have been doing all this while. And so I will have my first, that will be ethanol, liquid ethanol. It's good to write the phase because you will know when you look up appendix B2, you'll be looking for liquid, not for the gas. Okay, now you have oxygen, you have nitrogen. Beside that, you have your carbon dioxide being produced, and you have your water vapor. Please write it as vapor. Yeah, so I'm going to have my first column. That's going to be N in, number of mole. I'm going to have my inlet enthalpy, that's kilojoules per mole. My outlet, amount of outlet, mole. Okay. And my outlet enthalpy in kilojoules per mole. I'm not going to draw well, I can if I want. Better not. Okay, let's put in the values that we have. That's 1 mole. Our oxygen just now we said going to supply 3. This is 11.28. I'm looking at the table over here. There's no carbon dioxide, there's no water vapor. And the amount coming out, there's no methanol, liquid methanol, 1.5, 11.28, obviously, because it's nitrogen, it's not participating at all in the reaction. That's 1, that's 2. Okay, what reference state are we going to use? Because remember, you have two methods of doing it. One of it is using the heat of reaction, the other method is using heat of formation. So which one do you find easier?
Heat of formation.
Heat of formation. Somebody else? Ibrahim?
I think heat of reaction.
Heat of reaction. Okay, you can use either way. Which one that you are confident with, stick with it. Unless the question specified that it must be done in a particular method, then you have no choice. You have to stick with that instruction. Okay. So since we already have here written the extent of reaction there, okay. But if you want to proceed with heat of formation, you still can use the extent of reaction to solve the material balance, no problem. But since I already have the extent of reaction, how about we stick with heat of reaction? So I'm going to choose CH3OH as my reference state liquid, my oxygen gas, my nitrogen gas. You can use either way. I'm just doing this way. If you have ample time, just do it the other way. Okay, double check whether you're going to come up with the same answer. Carbon dioxide gas and water vapor, the temperature should be at 25 degrees C and 1 atm. That's your reference temperature, pressure, sorry. Okay, so now, since it is at 25 degrees C, 1 atm, you can get this enthalpy for methanol. What is it?
0.
0. Why?
Reference system.
Yeah, because it is at the reference temperature. The outlet, the air is coming in at 100 degrees C. Right? So at 25 degrees C. So this is going to be 0. And how to get the value for nitrogen and oxygen? Anybody? At 25 degrees C, 1 atm, reference state.
Use table B8 and use the integration.
Okay, we're going to use the table B8 because the reference state is the same as that of table B8. Okay, oxygen, gas, and nitrogen gas is listed in appendix B8. So let's look at appendix B8. If you are using the heat of formation, you still can use appendix B8 because oxygen and nitrogen is in its elemental form. Okay, your reference state is still oxygen and nitrogen. It doesn't change because it is in its natural state. So actually undo that. So let me clear this table so that everything you can see it. Yeah. And now your A is coming in at 100 degrees C. You have oxygen, you have nitrogen. So I'm going to write that down because that's the value we need in our enthalpy table. So 2.24 for oxygen and nitrogen 2.19. So let's go back to our example. So for oxygen just now is 2.24. For nitrogen, 2.19. But unfortunately, you cannot get the enthalpy for the outlet stream because you don't know the outlet temperature. So you're going to give it a symbol of, for example, that's 1, that's 2, that's 3, and the capital H with a cap, that's 4. This is going to be, you're going to integrate it from 25 degrees C. Why 25 degrees C? Because your reference state starts at 25 degrees C. Your reference state is at 25 degrees C and the temperature outlet is the unknown. So this is your adiabatic temperature. For 25 degrees C, that is your adiabatic temperature. Does the question ask for adiabatic temperature? It just says the highest possible temperature. So that is the adiabatic flame temperature. 25 degrees C, the adiabatic flame temperature. That's 25 degrees C the adiabatic flame temperature. So this will be the CP for water vapor, CT. That's going to be the CP of carbon dioxide gas with respect to temperature. This is going to be the heat capacity of nitrogen gas with respect to temperature. And lastly, that's the CP of oxygen gas with respect to temperature. So if you're going to use the heat of reaction method, your final equation is going to be, after you have written the full equation, please write the full equation. You need to write the full equation. You need to specify why the change in kinetic energy is 0, the change in potential energy is equal to 0, and why the work shaft is equal to 0. You need to give a reason. This is going to be 0. Why 0? Because it is adiabatic. When you are going to get the highest possible temperature, that is going to be 0. This is going to be your extent of reaction times by your heat of reaction plus the summation of your outlet, the product of your molar flow, your molar rate with its enthalpy minus the inlet, the molar rate, and its enthalpies. Right? So now, what is your heat of reaction? The one that I have written over here, I did not write whether it's vapor or whether it's gas, whether it's liquid or whether it's vapor. The equation I have over here, that I wrote over here, I did not specify whether your water is going to be liquid or gas. I'm going to write it down here again. I'm going to write it here. I have, what did I have written on? Liquid. First, let me copy it because I need to make sure that I got it balanced. 3/2 oxygen. I'm going to form carbon dioxide gas, and the amount of water formed is going to be 2. Anywhere can I get this source of heat of reaction? Anybody? Where can I get it from? I can calculate it directly if I want to, using the heat of formation or the heat of combustion, isn't it? Can I look it up using the heat of combustion? Anybody? Let's look in the appendix for methanol. Appendix B1 for methanol, liquid methanol. Can I use that information from appendix B1 to get the heat of combustion or to get the heat of reaction? And this is B2. I'm going to look at B1. Methanol is somewhere further up. Okay, that's methane. I don't want methane. I'm going to erase this. Erase that. Okay, I'm going to look at methanol. Methanol, that's methanol. Yeah, and the heat of combustion for liquid methanol. There should be a negative sign there. Okay, so that is the heat of reaction for methanol, provided, because this is the heat of combustion, provided that liquid water is being formed. So that's minus 7 to 6.6. So let's go back to our example. I'm going to write that. This is liquid water, so that is going to be minus 726.6. The unit is going to be kilojoules per mole. That is your heat of combustion, and that is so the same thing as the heat of reaction because that reaction is a combustion process. Yeah, so you get that. But since we already specified that your water here in its reference state is going to be vapor, so you have to get another heat of reaction when water vapor is being formed. Instead of liquid water, you're going to have water vapor. Or let me undo that. I'm going to have water vapor. What is my heat of reaction? Anybody? Anybody?
It's lower heat of reaction.
Lower. Remember 7 to 6 is from here. Plus NW44. Remember that formula? That's what we did now.
I got negative 638.574.
Okay, so that's 2 over 1 times by 44. Hold on. Let me complete this first. And it's going to be negative 600. Sorry.
38.57.
38.57. Thank you. Anybody? Can somebody double check on that? Is that correct? Double check on that. Is that the heat of reaction when water vapor is being formed? Is that correct? Somebody double check that calculation. Why am I doing this? Because I want to put that value here in this part of the equation. I need that value. Somebody double check, please. Okay, nobody is going to respond. I'm going to calculate it myself. Okay, negative 638.57. Thank you, 74. Yeah, same value. So that is going to be. Thank you very much, Nabila. Somehow you guys are the regulars. I don't know what happened to the rest. So now we need to get the polynomial equation, the CP for oxygen, nitrogen, carbon dioxide, and water vapor from appendix B2. I already got it written, so I'm going to put it in a table form so that everybody can see it. I'm going to go flip back to appendix B2. I'm going to write down the values so that you guys can see it. So I have A, B, C, D here. But instead of just A, B, C, D, I'm going to change it a bit. That is your type. That's the heading. This is for oxygen. You got it very oxygen. Very the height is quite big for oxygen. Now that's nitrogen. That is carbon dioxide, and lastly my water vapor. Yeah. So I'm going to have my number of mole out. I'm going to write it here. You will see why. The number of mole out just now for oxygen is 1.5 mole. Nitrogen 11.28. Carbon dioxide is 1. Water is 2. So now is A, the polynomial value, the coefficient from appendix B1 to B2, sorry, that's 0.021. I'm not going to time it times 10 power of negative 3. I already convert it here. 0.029, 0.03611, 0.03346. That's your A. I'm going to have my B over here. I'll make a bigger space because it's times 10 power of negative 5. It's B. Then here I have my C. That's C. And lastly, my D. That's going to be, this is obtained from the appendix B2. You should know where is it because we have been using a lot of it. You can double check the values by looking at the appendix. By looking at appendix B2. 0.688 times 10 power of minus 5. The reason I'm doing this is I will show you why. It will be easier to do the calculation when you have everything listed down in this table form. I need to look at the time. It's already 3:30. D 1.311 times 10 minus 12 minus 2.871 times 10 power minus 12. To complete this. And lastly, 3593 times 10 minus 12. Okay. So what I'm going to do is I'm going to get it multiplied. I'm going to multiply. These are the CPs, right? These are the CPs. Isn't it? The CPs. That's a polynomial equation. I'm going to multiply it with my number of mole. Why am I doing it? Why do I multiply it? Because when I do the calculation, this is what I'm doing. Let me highlight it. This is it. The number of mole times by the enthalpy. And the enthalpy is in the form of integration. This is the integration. So I need to multiply this with this part. And the same thing I need for carbon dioxide with its corresponding CP. For water with its corresponding CP. For nitrogen, I need to multiply with its corresponding CP. So that's what I'm going to do next. I'm going to multiply my CP with the amount of mole for that each component. So when I do that, you can see later on, it's easier, but it's just that it's too time consuming because I need to I need to construct my table. So for oxygen, I'll be doing it all over again, but this time I'll be multiplying my CP, my polynomial equation, with the number of mole in the outlet for that component. That's what this carbon dioxide is just a bit time consuming because I need to construct my table. Lastly is the sum, which is the outlet, which is N times by its corresponding enthalpies, the outlet. Okay. Okay, so this is N times by A, N times by B, N times by C, N times by D. So you do this, you multiply this value of N with this value. You do the same thing over here, you do the same thing over here, and you do the same thing for D. So once you have done that, you come up with these values. That's one. I'm just going to jot everything down. You can double check my calculation whether I make any mistake. I'm going to rush through this because we have only a few more minutes left. So when you sum it up, the first column, when you sum it up, it's going to give you 4738. For the second column, 9.8265 times 10 to the power minus 5. When you total everything up, in each column, you total everything up, you come up with these values. That is the summation of the outlet. So that is the summation of the outlet. So that is this part of the equation. That's the outlet. The inlet, obviously, you just do this, that multiply that, and this multiply by that. That is the inlet. So that is your inlet. Yeah, your inlet is there. Now, put everything inside this equation. Put everything inside this equation. We will come out with one unknown, which is the temperature. But unfortunately, it is in the form of integration. So let's do that. I have over here, that's 1. Okay, that's my extent of reaction. I got 1 just now. Okay, 1. And my heat of reaction, I got that. Minus 638. So that's going to be minus 638.57. Yeah. For this part is the integration that I have from 25 to the final temperature. And the CP is that CP. Which is this CP? Let me highlight it. That is the CP. And that's the CP that you're going to put inside this equation. Inside here, this part of the equation. Yeah? And then this part, the inlet is obviously you can get the value. So let's do that. I'm going to do.
Doctor,
Yes.
the value of Q will equal to 0, right?
Yes.
Okay, thank you.
Okay. Q dot equals to 0 equals to, I'm not going to write I'm just going to go straight. Extent of reaction is 1. Yeah, 1 times by the heat of reaction just now is negative 638.57. Okay, plus the product of your outlet stream, the summation of your outlet stream, which I already multiply here. This is my number of mole. I multiply for every polynomial equation. I multiply with that. I multiply with that. I do the same thing for C. I do the same thing for D. For that value, I do the same thing for A, B, C, and D. And lastly, for our water, I repeated the same process. For A, B, and C, I multiply each of them. I come up with that table. And that the final value after you sum the whole thing here. Sorry, I should not go all the way down. After I have summed this whole thing up, I come up with the final value, which is the last row. So now I have a summation from 25 degrees C to the final temperature, which is repeating that last row, 0.74738 plus 9.8265 times 10 to the power minus 5. That's T temperature plus 4.1779 times 10 to the power minus 8. That's T square. I need to continue down here. Sorry, I should be minus, not plus. Minus 30.1291 times 10 to the power minus 12. That's T to the power of 3 with respect to temperature. So that is the outlet, which is, I highlighted it over here. That's the outlet. Yeah, now the inlet. The inlet I'm going to look up from the table here. 3 times 2.24 minus 3 times 2.24 plus for my nitrogen 11.28 times by 2.19. That's 11.28 by 2.19. So that's completed the whole thing. So now all you have to do is once you have done the calculation, let's see. I'm not going to repeat this whole thing, so I'm just going to put it there. Equals to, so if you do the calculation, bring it over to the right hand side, that minus sign is going to be positive. Okay, so your 3 times by 2.24 is going to be positive. When you bring it over to the other side, that's going to be positive. Your plus 6.72. This is that value. And so if you multiply that, well, it becomes negative, but when you bring it over to the other side, it becomes positive. That's going to be 24.7032. So that is with respect to temperature. Okay. So now, somebody who has the calculator, can you get the temperature directly from your calculator?
Doctor,
Yes.
I got 1,256.7.
Thank you. Let's check the solution in the textbook. This is example 962. The answer from the textbook is 1256. Exactly, 1256. That's the solution in the textbook. That we got the final answer. Any questions? It's quite long because we have to multiply the outlet mole with its corresponding polynomial values, the A, the B, and the C, and the D. So you come up with the final equation, which is in this last column here, the last row here, which I highlighted already. So it's not that difficult to get the final temperature. It's just that you need to know how to use your calculator. Not many people can use the calculator because you have to have an engineering calculator to do that. So that is the final temperature. The outlet temperature, the highest possible temperature, 1256. That's very high. So your furnace must be able to withstand that very high temperature. If, for example, you design your furnace that cannot withstand that temperature, obviously you're going to have a meltdown. Any question on how to go about this problem? It's very straightforward. In fact, we have one example before this. It's similar to this method, except that it's asking for the T outlet, not the maximum possible temperature. It's not combustion. I forgot what example was it. We just touched lightly on it because we did not go in depth. We just touched it lightly. I forgot what example was it. You can look at this inside the textbook. Any question on this example? Anybody? Any questions?
Doctor,
Yes.
could you please share this slide in the WhatsApp group?
Wow. Okay. The problem is I'm using my iPad, and iPad doesn't have WhatsApp. I think I can use the browser, but I'm not sure whether I can use the browser to open WhatsApp, but I'm not sure whether I can import it to WhatsApp. Because if I'm using my handphone, I know I can import it to WhatsApp. What I have to do is just, share. I can do that. That remind me, your second test is already available. So I'll be starting to distribute your answer script back to you guys by tomorrow. And also your third assignment is already uploaded in e-learning. That will exist. Your third test is coming soon, next week on the 20th. So you should be doing your assignment also. And looking at the back of the chapter, the textbook at the back of the chapter. I will try to get this uploaded in WhatsApp. That means what I can do is I'm going to snapshot the screen of my iPad using my iPhone, and then I will, I can have it in WhatsApp then, because my phone, I can easily just snapshot it, and in WhatsApp, I can show it in WhatsApp. So anything else? Any other question besides having this whole thing shown in WhatsApp? It's quite messy, isn't it, the way I write everything? I hope you can see what's going on. Oh dear. I hope you can understand. It's really messy. I did not do it neatly. Okay, anything else besides having this solution posted in e-learning? Anything else? The method that I'm showing here, using the table method, is just to make it easier so that you do not make any mistakes. Because you have it, written in a table form. It's very visible. You just, sum everything in a column, you come up with the final equation. But if you don't know how to get your answer using integration, for example, you don't have that calculator to solve it directly, what you can do, I would suggest it be a try and error method. So over here, instead of doing the integration, you use table B8, and by try and error, get a value of, for example, I'm going to just press right down here. let's I'm going to write. Let's the first trial test T out equals to T adiabatic equals to 1200 degrees C. From there, you should be able to get the enthalpy of oxygen outlet out, enthalpy of nitrogen gas from appendix B8, and of carbon dioxide gas, because all these values, they are available in your appendix B8 because they are in gaseous form. So your reference state is the same as that appendix B8. So you should be able to get the value. So let me put in the values that I got earlier. For example, for oxygen, I make sure I got everything in the same sequence here. Oxygen, nitrogen, is it same? Oxygen, nitrogen, carbon dioxide, water. I hope it's this. Okay. Let's put in the value. If I make a mistake, please double check for me in appendix B8. That's kilojoules per mole. If you're going to do by try and error, if you cannot do using integration unless it's specified, just like the second test, that you must solve it by integration. For in this case, if it's not mentioned at all, you can do it either direct calculation using integration, or you can do it using try and error method. So this is your try and error method. So you put that. So once you have these values, and now what you have to do is put it inside your equation. That is your equation. That's your equation. Put it inside your equation. If your answer is not equals to 0, then you know that is not obviously not the correct temperature. Then you do another trial. So let's T out equals to T adiabatic equals to 1300 degrees C, for example. You know that it's going to be very high. It cannot be very low. It has to be above 1000. So you definitely going to start with some 1000 over. But if you do this, look it up from appendix B8, come up with that value. Okay. Well, I'm just going to hurry up. For nitrogen, 40.97. Then for carbon dioxide, that's going to be 65.8. And lastly, for your water vapor, that's going to be 51.47. Again, you do your calculation using our energy balance, which is that equation. Okay, that equation, you do your energy balance using that equation. And if it's again, it doesn't turn out to be 0, then you just interpolate between these two temperatures. You know, it's going to be somewhere between these two temperatures because it's 1005. But obviously, in this case, I know what is the temperature already, so I know it's going to be in between that two temperature. But if for example, you know it's no way close, then you go to the next trial. I think 3 times would be just enough to get the correct answer. 3 trials. This is a bit long because it's by try and error. But if you do it directly using integration, you can solve it directly using your calculator. It's just a matter of whether you know how to solve it directly using the calculator. So guys, it's already 3:50. Any questions on this example? Any questions? I have one assignment, assignment 3, one question that is something similar to this example, whereby you need to calculate the outlet temperature of this combustion process. Is one of the question in one of the assignment. I mean in assignment number 3. Any questions?
Doctor.
Yes.
For testing until where is coming out?
Sorry, can you repeat that again?
For test 3, what are the subtopics are coming out?
What are the stuff coming out? The topic coming out is it's chapter. Sorry, it's chapter 9.
Yeah. What are the topics are coming out?
Okay, chapter 9.
Okay,
chapter 9 is what we have covered so far. Till this topic, I don't think it's coming out on this adiabatic, but then obviously not the adiabatic temperature, but obviously you're going to get the outlet temperatures. The one of the example in your textbook, there's one outlet temperature example. So it could be possible that so far what we have covered is what is coming out. I don't know what is coming. I mean, the topic that is coming out is what we have covered from the beginning of chapter 9. Who's going to set the question? Dr. Azizul and Dr. Ahnizam. 3 questions, as always.
Okay, doctor. Thank you.
Okay, so please do a lot of do my assignment, and then do the problem at the back of the chapter. Okay, now I come across the temperature. The temperature, the example is example 953. Example 953 is almost similar to this method that we are looking at, that we just look at. Example 953 is asking for the outlet temperature, the product temperature. I remember we did that. Example 953, this is it. We did not solve it. We just mentioned how it should be how to go about it. Yeah? We did not solve it. We stopped there. But this is similar. This method is similar. What we have just gone through is similar to how to solve this example 953. So you can also try this method on example 953. Anything else besides about the third test? Anything else? No? Nothing? Okay guys, thank you very much for your attendance, and I will upload this. I will snapshot it so that you can have a look at it in e-learning, but there are some of it is quite messy, so I hope you be able to follow the steps over here. I cannot erase the circle that I have done, because if I erase that, I will be erasing some of the stuff that I have written. So it's quite messy, really. So anyway, thank you very much. Do
Doctor,
take care. Yes, please. Anything?
is it okay if you share the attendance again?
Oh yes, I see. Definitely, it's okay. Just let me try to get the screen. Okay. I'm not sure what's wrong. The academic UTM.mine refused to connect. Why is it? Can I deactivate it? I can't. Okay. How you can somebody just okay. Okay guys, so thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and take care of yourself. Somebody just got positive, our UTM student SKT. I'm sure the Arab student know who it is. Yeah, take care guys. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Welcome.
Thank you, doctor.
Most welcome.
Hello.